Hello, everyone. I'm Laura Riello from the IEEE Electron Devices Society Executive Office. Welcome to the EDS webinar on vertical thinking in light emitting diodes. A few housekeeping details. We will have a Q&A session after today's talk. If you have any questions for our presenter, please use the chat window located on the right-hand side of your screen to share your questions with our presenter at the end of the session. I would now like to introduce today's speaker. Professor Can Bayram is an associate professor in the Department of Electrical and Computer Engineering, a resident faculty at the Nick Hollenack Jr. Micro and Nanotechnology Laboratory, and an affiliate faculty of the Carlisle, Illinois College of Medicine and Healthcare Engineering Systems Center of the University of Illinois at Urbana-Champaign, Illinois. He is an expert in 3x5 materials and photonic and electronic devices. He has performed more than 3,000 plus epitaxial growths with metal organic chemical vapor deposition systems and fabricated detectors, light emitting diodes, solar cells, resonant tunneling diodes, and transistors in class 100 and 1000, clean rooms totaling 20,000 plus hours equipment usage. His current research interests lie in intersection of novel 3x5 materials, heterostructures, and photonic and electronic quantum devices. Particularly, his research group explores 3x5 materials and novel devices, heterojunction integration of 3x5s on unconventional platforms such as graphene and silicon, heat transport across through semiconductors, efficiency droop mechanism, and remedies in halogen emitters, and ultra-fast THZ photonics electronics. Professor Byman's work has been recognized widely. He is a recipient of the International Union on Pure and Applied Physics Young Scientists Prize in Optics, IEEE Nanotechnology Council Early Career Award, an NSF Career Award, CS Mantech Best Paper Award, an AFOSR Young Investigator Award, the IEEE Electron Devices Society Early Career Award, and a Best Paper at the 11th International Conference on Infrared Optoelectronics. For his achievements in ultraviolet 2 terahertz engineering of 3x5 semiconductor materials and devices, OSA, SPIE, and IEEE recognize him with senior member status. Professor Bayram supervised or is supervising 3 to 4 PhD theses, 1 MS thesis, 5 senior thesis, and authored 53 journal papers, 39 conference proceedings, and 2 book chapters, along with over 47 patents issues that are pending or issued. It's my great pleasure to introduce Professor Can Bayram.
Thank you, Laura, for the kind introduction, and thank you very much for the invitation. And good morning, good afternoon, and good evening, depending on when and where you are joining us. I am Can Bayram, a faculty at University of Illinois, and as you may know, this week is the Thanksgiving week. I'm currently on sabbatical leave in Middle East Technical University, Turkey, and today is Teachers Appreciation Day. So I just want to thank to all teachers who made our today and who are going to shape our future. Thank you all. Now, today I'm going to talk about LEDs. This is a topic that you are most likely familiar with. Since the invention of first visible LED by our colleague Professor Holonyak, there has been a vast research and development in this area. With the recent awarding of Nobel Prize in 2014 for the blue LEDs in use of white lighting, there is another renowned exploration. Now, what I'm going to talk to you about is not only the conventional LEDs, but also how we can go to the next stage in these devices. So my group works on 3 different core topics, from lighting, RF to power, and today I'll be mainly talking about lighting and light emitting diodes, and that's the most mature technology in gallium nitride related materials. Now, when we look at the photonics, of course, we have a diverse range of applications from detectors to emitters. Now, looking at many of these applications, what we can notice is that it's the wavelength tunability that is very important. For example, for disinfection purposes, you need high energy UV, but for lighting, you need lower energy, more safe emission spectrum. And of course, you need to control the power. For some applications, you need more, for some, you need less. So it's all about controlling the power along with the wavelength. When we look into the materials we typically use, it's basically based on from periodic table, column 3 and column 5. Here you can see aluminum, gallium, indium with column 5, phosphine, arsine, and antimony. And here is the band gap energy as a function of lattice constant. Now, if we mix indium and antimony, we get indium antimonide. And looking at the band structure, we see that the top of the valence band is aligned with the bottom of the conduction band. And this is a direct band gap material with a relatively lower band gap. Now, if we mix aluminum and phosphorus, we get aluminum phosphate. And when we look at the band structure, we see that it's the wider band gap, but this material is indirect band gap. Now, what we do is, in my group, we introduce a new element, column 4, from column 5, nitrogen, so that we can expand this band gap energies. By just putting aluminum with nitrogen, we can tune in the entire UV spectrum by just adding gallium. And further adding indium pushes this through the entire visible spectrum going to the infrared. So with the introduction of nitrogen, we can enable higher spectral control and energy. Now, in the first topic, I am going to discuss about a very recent technology that really drove our attention, germicidal photonics. Now, if we look at one of the most important global health problems, that's child mortality. Here is the map that shows underage 5 mortality rate. And you can see how it is mostly populated in underdeveloped countries. Now, if you look at these numbers, the numbers are strikingly high. Annually, we have close to 7 million child mortality due to a different type of reasons. And the two out of the top most reasons are waterborne diseases, diarrhea and pneumonia. Now, children under age 5 are more vulnerable to these microbes because they don't have a fully developed immune system and we don't have appropriate medication. So basically, by just disinfecting these water sources, we can just save 1 in 4 child. Now, how does this technology work? When we look at the absorption spectrum as a function of wavelength for DNA, you can see that it peaks in the UV spectrum. Now, we already used UV-based disinfections in hospitals through arc lamps, where you have high voltage, basically metal plates, creating these broad spectrum emitters. We also used to use, which is being phased out because of environmental and safety concerns, mercury lamps, but they have a specific emission wavelength. Now, what is important to notice, for some bacteria or viruses, we do not have DNA, so we might need to target membrane protein or enzymes. That requires different kind of optimum wavelength. So basically, the available technologies cannot target specific enzymes or different proteins. So it's important to have tunability. Now let's look at the importance of tunability. Here we have reduction in E. coli bacteria in logarithmic scale as a function of wavelength of elimination. You can see that a slight change in the source increases the count of bacteria logarithmically. And this is for a specific flow rate underwater. And for E. coli, 280 nanometer is the peak disinfection wavelength. Now, what is a UV LED? So a UV LED structure is shown here. And of course, this is basically a P IN structure on a substrate, and we have lots of buffer layers to engineer and reduce the defect densities, but mainly the emission is coming from multi-quantum well. So let's take a closer look. A multi-quantum well is basically a barrier sandwiching a well. So we have parameters such as aluminum content of the well and barrier and thickness of the well and barrier controlling our primary design. Now, by just looking at the aluminum content of the well using Weger's law, we can calculate the bulk component contribution to the emission, which is written here. By looking into the aluminum content of the well and barrier, we can calculate the band offsets, and given the length of the well, we can find the quantum contribution to the emission wavelengths. And by looking at the aluminum content of the well and barrier and considering the polarization nature of the system, we can look at Stark effect contribution that comes in this term. So basically, even by just hand calculation, we can design these structures, and here is some experimental results at 280 nanometer per the design. Now, 280 nanometer is designed for E. coli, and this can easily be adjusted by the same design mechanisms to target DNA at 265 or other enzymes such as NADH at 340. Now, these discrete components are really small, and we can just package them into arrays for higher power output. And the biggest part of these systems you can see is the battery. So the battery is the biggest part in many of these applications, not the semiconductor part. So it's in principle using solar power systems, solar cells, where the underdeveloped countries have, as you know, in Africa, lots of available sun power. We can easily disinfect and save and reduce child mortality rates. Now, how can we go beyond these conventional LEDs? Here is the lattice structure of an LED. Basically, it's a Wurtzite structure with gallium and nitrogen connected. A here is the lattice parameter of the base, and C is the lattice parameter in this direction. Now, these galliums and nitrogen atoms are connected in tetrahedral arrangement. So they basically, because of their different properties, they have a spontaneous polarization between due to electronegativity. And overall, because of the angle and the bonds, it has an inherent spontaneous that exists in the material as is polarization field, and this depends on the composition, meaning that aluminum gallium content. Now, in typical structures, we are growing them on different substrates. We are having quantum structures with different lattice constants. So these structures are typically under stress, creating a change in the lattice constant like A prime, C prime here. Because these materials are piezoelectric, you also get a piezoelectric effect depending on the stress. That could be lattice or thermal mismatch. So overall, there is a significant effect of polarization fields, and it's very important to eliminate the polarization for next generation devices. So here is the normalized efficiency as a function of injection current, a UV LED. Now, when we look into this, we see that the efficiency peaks under low current densities, and the efficiency drops when we increase the injection. This is called efficiency drop. If we look for blue LEDs where we use more indium rather than aluminum, or green LEDs where we use more indium, we see that the drop just increases. Now, if you look into red LEDs based on arsine phosphine technology, we do not see similar effects under these injection levels. So what's the difference? So first of all, UV blue green is based on nitrides, whereas red LEDs is based on arsine phosphine material family. So nitrides are piezoelectric, they are polar, they are they have six-fold symmetry, hexagonal or Wurtzite crystal structure, whereas arsine phosphine family do not have polarization. They are symmetric, they are cubic in the growth direction and in zinc blende form. And aside from it, technologically, conventional nitride LEDs are grown on typically insulating substrates, so you have lateral configuration where you have two contacts on one side. But for arsine phosphine, the conductive substrates are available, so vertical structure can be enabled. So in the future, why not we use this know-how and create non-polar vertical UV blue-green LEDs. Now, one way of doing this is switching the material phase from hexagonal 6-fold symmetry to cubic 4-fold gallium nitride high symmetry system. So the band gap of cubic nitride is 3.2, and it's a direct band gap. It has much better mobility values, higher symmetry, and lower activation energy. So you can achieve higher injection, higher doping efficiency, higher overlap integral because of the non-polar nature, and higher drift velocity, ideal for devices, and higher optical gain, lower laser threshold. And you can cleave these layers because cubic has the cleavage plane. It's much easier to make laser cavities, and theoretically it's shown they have lower Auger coefficients due to the higher symmetry. So you can go to almost drop-free structures. So when we look at this, cubic nitrides have a lot of advantage. The historical challenge has been synthesizing reliable cubic nitrides. So this is what I'm going to talk about currently. So if we try to grow gallium nitride on conventional silicon 100, this is how it looks like. Basically, it's non-selective process, multicrystalline, random, and multiphase. Now we have developed a process where we can selectively nucleate these structures, have single crystal, single phase, and controlled. And we demonstrate this over large areas. Now what does this mean? This means that we can use the selective nature in some sort of an aspect ratio patterning structures. Now the aspect ratio patterning structure shown here is commonly used for arsine, phosphine, and germanium family. Mainly you have silicon dioxide sidewalls on top of a silicon 100 substrate, and the defects follow the growth direction and they get terminated. Basically they get stuck in the sidewall and the top layer is defect free. Here you can see how defects are localized to the bottom of this arch structure, aspect ratio trapping structure. Now what's interesting is if we pattern this substrate to make what we call a U groove and exposing silicon 111 facets, we have a different type of defect formation, and we notice that we have a material change after these facets meet. So let's look into this in more detail. Mainly, a 6-fold symmetry and 4-fold symmetry has a common direction. The Wurtzite 0001 direction is the same direction as cubic 111 direction. One way to look into this is if you have a cube in your hand and if you rotate it, you are going to see an hexagon. So this is what we are using. Basically having two growth fronts coming together with the perfect angle is going to switch to cubic phase organically and naturally. So from the X-ray, we can see the emergence of cubic nitride, and from the incoming facets from the selective area electron diffraction, we can prove that the incoming facets are Wurtzite and the resultant structure is zinc blende. And here is the phase mapping that has accuracy of 20 nanometers. So we have mapped these groove structures and show that the incoming phase is Wurtzite and the resultant phase is zinc blende. And here's a top SEM surface showing 100% cubic surfaces. And this is the basically atomic resolution showing the stacking formation that enables the phase transition. Now, this material is important because by adding more aluminum or more indium to go to UV or visible spectrum, you are non-polar, so you can increase your recombination dynamics significantly. And by proper design, you can you can lower the needed aluminum as well as needed indium content in these different spectrums. So overall, going from a 6-fold symmetry Wurtzite structure to zinc blende really increases our overall recombination dynamics and efficiency. So we recently demonstrated about 29% internal quantum efficiency in these structures that are stable and they are virtually stress-free, crack-free, and low defect density and no electric field with cleaving layer. And also we use a very almost aluminum-free buffer structure. So the next part is getting these devices so that we can really enable an interdigitated light emitting diode suitable to cover this deep UV. Another application could be to shape these grooves properly to have UV laser diodes, electrically injected UV laser diodes, where we have higher gain characteristics and better injection properties. So getting to higher efficiencies in the UV spectrum is critical for disinfection purposes, considering different kind of biothreats, either from air or water. So it's very important to come up with innovative designs where we use polarization-free structures, less aluminum, less indium, less aluminum, and less mismatched structures, and scalable approach with silicon considered in hand. And cubic nitride is one of these potential applications. Now, next, I'd like to talk about our daily lives, visible LEDs. So we see LEDs everywhere: internal, external illumination, displays, backlighting. Now, these applications have different power recommendations. Lower power needs for illumination, much higher for displays, and of course, the holy grail, general lighting with the most power need so that we can have convenient reading and activities. Now, this is an interesting chart. This is showing the average household energy consumption estimates for lighting on the left, and you can see as a function of year here. So Department of Energy estimate shows that with the introduction of LEDs, the need or the use of light consumption has decreased already. However, because of the lack of adoption as well as um, increase in lighting use with the increase in spaces and the reduction in cost, the light consumption is increasing. This is very interesting. Now, if you look at the models, predicted models, where the models assume almost all LED penetration, we see that we expect almost an exponential like increase in lighting needs because of either the costs going down in lighting in LEDs, or we using larger spaces under illumination. So overall, if we cannot push these LED advantages to where it should be, we are going to see exponential use and increase in lighting. Now, of course, solid-state lighting has other applications aside from energy savings. You can control spectrum, you can control polarization, color temperature, modulation, emission. So these are very important for more further energy efficiency as well as comfort, as well as increasing productivity. Now there are more emerging opportunities in micro LEDs, in horticulture, with space exploration. We might be growing our own vegetables maybe in our rooms. And with the introduction of VR and also the meta world, there is a growing need for connected lighting services, sensing, as well as even integrated photonic applications where LEDs might offer a low threshold solution. So my group works on these different type of LEDs, and we fabricate a variety of structures using our facilities from blue to green. What I'd like to focus on is the need for a green LED. So when we look at the efficiency of these LEDs as a function of wavelength, we notice that with going from blue to green, we put more indium and your efficiency goes down significantly. So typically, the white lighting schemes involves a blue LED that comes from indium gallium nitride material system with a phosphor, so that you can create the yellow light and you receive what we call a warm white structure. Now, ideally, the most efficient way of color mixing is three color mixing, blue, green, red, where you need three LEDs, blue, green, red. And again, blue LED is the Nobel Prize 2014. Red LED is invented by Professor Holonyak. Now, although we have the blue LED from indium gallium nitride and we have the red LEDs from Professor Holonyak's work, we do not have a high efficiency green LED to work to enable color mixing. Now, this situation is worsened by our eye response. Because of eye having the peak responsivity in green, because of the incoming sun flux, we notice when there is lack of green in these LEDs. So overall, having these kind of three color structures under most efficient lighting scheme will provide the most energy efficient solution and best color choice for our health as well as productivity and future. Now, let's look at the origin of green gap. So again, an LED is basically a PIN structure where the active layer is a multi-quantum value. So what I'm going to show here is basically if you have a green LED, you typically have 25% indium. And here are some results of high resolution TEM of these LEDs, where you can see the indium is scattered around. So the average indium content is 25, but you have indium rich regions with 45% and indium poor regions with 10%. Now, if we grow these structures without the capping, without the p-GaN layer, we see that indeed our indium is uniform as grown. So what's the problem? So the problem is basically higher temperature of p gallium nitride. So this is because of the chemistry of the system as well as deposition techniques. You increase the temperature from quantum well to the p gallium nitride, and mainly your high indium content and the diffusion, thermal diffusion out of these indiums in your quantum wells creates non-uniformity and performance problems. So the question came, can we reduce these growth temperatures? Well, if you look at the energy lattice constant diagram of nitrides, we see that there is a material, zinc oxide, that has the same crystalline structure. It's lattice matched in the indium content solutions, and you can have better light extraction, and it's non-toxic and it's inexpensive. So one of our designs employed zinc oxide on top solutions where we achieved one of the purest green emitters in terms of spectral quality. And because of its cost, this was also adopted by OSRAM for the production light, mainly used for the blue LEDs because of reduction of the cost. So this is one feature that could be very interesting to have use of green LEDs with innovative solutions. Right now, we are looking into using cubic indium gallium nitride materials. So theoretically, we have studied many of these structures, and we saw that cubic nitrides require at least 5% less indium. They confine carriers better in the active layer because of the larger barrier. They can achieve higher p doping, and this has also been shown. And you can achieve much higher internal quantum efficiencies because of the lower Auger coefficients. And overall, based on our design, you can create a path to LED structures where you emit more light than heat in the green spectrum. So this is very important. So this all depends on, of course, the synthesis of a cubic gallium nitride material. And this is the structure where we are using what we call a U groove, where we have the oxide with a thickness H, exposed silicon 111 facet 100, and then a slight sidewall angle, which is based on the process parameter. So basically, if we can design these structures, we can achieve pure cubic nitride systems. Now, basically, when we look at the processing of these structures, we start with a silicon 100 wafer, and here we are zooming in into the structure. We are first growing our oxide, thermal oxide, CMOS compatible process, and then we are going to shape our oxide using the photoresist and opening, and then we are going to remove first deposit a hard mask to have a better vertical sidewall, and then we are going to remove the oxide and expose silicon 100, followed by the selective wet etching. This is the advantage of wet etching selectivity between 100 and 111. And then we are going to start our selective deposition technology, where we can nucleate hexagonal gallium nitride on silicon 111 facets, and when they meet crystallographically, organically, naturally, the cubic gallium nitride forms in the groove and continues to grow as follows. So overall, we have demonstrated a successful demonstration at scale of these cubic nitride structures. So here you can see a catoluminescence result showing how cubic gallium nitride is starting dominating the surface as we continue the epitaxy, and we showed efficiencies of 29%, whereas hexagonal GaN under the same conditions is about 12%. So 2.5 times more efficient structures. And when we look at the defects, we can see that the top layer is virtually defect-free as we know it. And here you can see the atomic resolution of these gallium and nitrogen atoms. And we have demonstrated this on chip scale, 1 centimeter by 1 centimeter scale. And there are a lot of exciting work from also different groups that shows that the indium needed in these structures to achieve the green wavelength is even 10% or less than the hexagonal counterpart. So basically, by just using cubic nitrides, we can reduce the indium content and indium thermal diffusion and other things, of course. And our own designs also show that by going to a thicker quantum well, because of the nonpolar nature of the structures, we can basically reduce the number of quantum wells and enable very high efficient green LEDs. So this work, of course, has been supported by multiple venues from NSF, NASA to ARPA-E, and we recently formed a company to make these templates structures available for everyone so that we can really get a much better solution for lighting and scalable solutions. So here are some of the structures where we have large area synthesis of the structures and the final templates where we can build onto freestanding wafers, LEDs, or laser diodes. Now in the next part, I'm going to talk about an exciting part basically on thin film devices. One of the best advantages of visible lighting is, it doesn't hurt us, at the levels that we are exposed. So it's used in medicine a lot. It's used in imaging retina, looking at the different cells by using color tuned proteins, and it's even used in guided surgery. So basically, you can pinpoint the cancer cells so that you can just you can laser remove these cells. And recently, with the development of the genetic field, it's even used to study brain, looking into different parts of brain where we see the impact of depression, and it can even be used to secrete hormones such as insulin on demand. Now, how does this technology work? So basically, the optogenetics is the combination of using light with the genetic modification. So based on the opsins in the proteins of these what we call organisms in the sea, uh, we can we can basically simulate these opsins, light sensitive proteins that open up or close depending on which light you are sending in. So these opsins can be integrated into various of structures, systems, organic systems, and by using light such as blue light, you can excite, or yellow or red light, you can inhibit or stop pain. Now, what's most interesting to me is that all of these opsins proteins are responsive to the visible light. So basically, by just changing the indium content, we can have a different kind of response. So here you can see the first generation, what I call first generation optogenetics work, where the light is coming into the optogenetically modified brain by using an optical fiber, and the light illumination angle is, of course, limited because of the fiber optic. But note that, in brain, we don't know which part is really responsible for what function. So the entire brain needs illumination if we are going to study this kind of autogenetic experiment. There are concerns about this type of approach in terms of, it restricts the mobility of the study element, and it's also limited in terms of illumination properties like angle, area, wavelength, and efficiency of the system. The second generations use wireless systems, wireless receivers, where they are using light emitting diodes. And here you can notice that they have multiple LEDs and they have lateral configurated LEDs. And of course, because of the LEDs, the angle illumination is much wider, but again, it's not perfect. And depending on looking into the survival rates of these systems, the sensors such as temperature sensors and other sensors survive longer time than light emitting diodes. So typically there is an interest in creating these thin film conformal, much robust bio LEDs so that we can reduce the concern over lifetime use, lesion, and creating these kind of problem. And again, when we are talking about biostructures, heating is important, so we want to make sure that we do not increase the temperature of the system, biosystem, at all, if possible. So looking into conventional LEDs with respect to novel LEDs, the conventional LEDs are typically focused on more high power range, whereas novel LEDs really requires much less power. But the focus is more on the custom area and local heating. And bio LEDs requires to be really small and flexible so that we do not create any lesions during insertion or any irritation after installment. And of course, both devices have to be efficient. And for bio, more uniform illumination is important, particularly for optogenetics. And the lifetime has to be really long so that the patient doesn't need to be operated over and over again. So overall, there are different design rules for these type of LEDs. Now, the conventional way of having these thin film LEDs is basically through substrate removal. Typically, you have a lateral structure, and then you have a substrate that's optically transparent, and you are using laser and chemical etch. Now, in these lateral structures, what happens is typically you have always current crowding. The current chooses the lowest resistance path, and you have more current density here, and this creates not only heating but also as a reliability issue in the long run. So it's important to have vertical structures where the current can spread, the illumination is more uniform, and the heating is much, much less. And the typical way of removing substrate is, through laser liftoff, where the laser is coming in through the transparent substrate, and the buffer layer, the gallium nitride type structures, is becoming a gallium melt and nitrogen popping up the substrate. And this really limits the chip size as well as the yield. And what I'm going to talk about is a different way of removing the structure from the top, not from the bottom, so that we can achieve much thinner structures, much larger area, and with much flexibility. And I'm going to show that we have done this for 2-inch structures. And again, overall, I'm going to show thinnest LEDs in inorganic structures that can offer custom shapes and that can be flexible. And it's important to note that bending stiffness is proportional to third order thickness. So even if you halve, you are going to have significant flexibility. Now, this mechanical release technique is something that really we see every day. Typically, this is something that you notice if you are a homeowner or if you are just walking outside an old building. You might notice, paint is coming off the wall. Well, whether you are a homeowner or you are just you are just walking by, you might notice, when the paint is coming off, it also chips part of this wall structure. This is indeed called spalling, and this is called the failure mechanism, spalling failure mechanism. When you have a film under tension, you create a crack, and this crack also takes part of the substrate or part of your wall in this case. So the goal here is, can we create a structure where we can really control these opening modes and the propagation modes of these stress layers? So this has been done, as you can see here, for solar cells, 4-inch, where we demonstrated high specific power solar cells when it was published, as well as we have shown this on 2-inch thin film LEDs, as you can see here. Now, what you may notice here is when you look into nitride LEDs, you see that there are strict lines here, and this is because of the mode 3 effects. So the question is, can we really remove these kind of stress strict patterns, or can we even make these devices thinner? So the solution comes finding a perfect mechanical release structure, and that's where we introduced graphene as a mechanical release structure. So what I'm going to show you is the first use of GaN on graphene directly without any buffer layer. So we start with graphenization of silicon carbide, and then we deposit gallium nitride atop, and then we use a stressor nickel and use a tape to release it, gallium nitride from the graphene, and basically graphene stays with silicon carbide, so you can reuse it infinitely. And the remaining GaN, because the surface is very smooth, you can just bond it to anything you want. And I will show it on silicon. And you can just remove the tape and the stressor layers. So the conventional epitaxy of 3D materials depends on the dangling bonds and the bond interactions. And the van der Waals materials interacts with the weak van der Waals force, and you can stack them layer by layer. So what I'm going to show you is a new technique, 3D material on a 2D material. And I'm going to show this for the case of GaN on graphene. And again, if you try to grow GaN on graphene directly, this is how it looks like, multicrystalline non-uniform. We have come up with a process to grow a single crystal structure on top with roughness, which is, as you can see here, very smooth. And we proved that the graphene is still intact by the high resolution TEM studies, and graphene is still at the interface. And by selective electron diffraction, we have shown the crystallographic relationship between all these structures. And again, we grow GaN on graphene, and then we put our new stressor with the mechanical release. We released our GaN, and here is the Raman measurement of the gallium nitride. And when we look at the surface, which is basically the growth surface on the graphene, that's the reverse structure, we see that this surface is very smooth. Now, this is not possible by any other technique. And this is so smooth that you can just bond it to anything. And here you can see GaN on insulator, meaning that GaN on silicon dioxide on silicon, on O structure. And this is one of the, again, thinnest inorganic structure, and then you can make a lot of different devices similar to silicon on insulator technology. Now, what's interesting is when we look at the host substrate, we notice that graphene stayed because of the energy bond. Now, the graphene, because it stayed, we can reuse this, and we have reused this multiple times, and graphene is always there, and we can basically grow these structures and release these structures. And in the last run, we have done light emitting diodes, and again, it's a PIN structure with the quantum well, and here is the X-ray diffraction showing the multi-quantum well peaks, the photoluminescence for the blue LEDs, and we release these structures as described and look at their electroluminescence and show that we have a blue LED as a thin film, and this is one of the thinnest LEDs in terms of inorganic LEDs. So overall, gallium nitride is a very interesting material. It can have a lot of impact in healthcare, use of ultraviolet rays for germicidal effects, as well as developing green LEDs for not only efficiency but also for health and productivity, and also for medical purposes. And to go to reach these goals, we really need to think creatively. So vertical thinking is very important here. Going polarization free, having an architecture which is vertical for better current spreading, and looking into different designs where flexibility is key. So I like to thank to my research team, and specifically I want to thank also my undergrads, where at Illinois we really take pride in our students doing a lot of the works, even as an undergrad. And I'd like to thank again to our alumni and those agencies and foundations and organizations recognizing our students, and of course all our funding agencies. So thank you very much.
Does anyone have any questions at this point? If you do, I guess if you can add them into the chat window. All right, it looks like we don't have any questions here, so I just want to thank you from the Electron Devices Society for offering to have your webinar. We really appreciate it. Oh, wait, actually there is a question in there. I don't know if you could say it. Did you say that ZNO is being used
Yes.
commercially for the P layer for LEDs?
Mhm. Yes. So basically, the zinc oxide is used in the structure such that the structure is basically inverted. So what I mean is, let me see here. So this is a inverted LED structure because, as we know, P zinc oxide does not exist today. So in order to demonstrate the concept, the proof of concept, what we have done is we have inverted the structure so that we have the P layer borrowed from gallium nitride and the zinc oxide is N layer. So the idea of this experiment is we never increase the temperature of the green quantum well above its deposition temperature so that the indium remained unscattered and not thermally diffused, leading to a very high spectral green LEDs. So the industry repeated this. Basically, they had a P-GaN first approach, and zinc oxide is used and typically as the top N layer for these purposes.
Okay. Yeah, I don't see any more questions. Okay, I'm wrong.
Thank you. Oh, I guess we have one more questions. So basically the question is about, can the cubic material be grown over the top of the trench? And this is certainly possible, and this is certainly the easy part, because this is similar to lateral epitaxial overgrowth, and we can easily grow on top and combine them. This is indeed one of our projects that's ongoing, and the biggest challenge of cubic gallium nitride effort in general is having a high quality base structure. The cubic GaN, if we look into in terms of technological development, was the one of the first materials synthesized on gallium arsenide and using magnesium oxide. However, the challenge there was the chemical incompatibility, such as arsenic diffusion at those temperatures, or a large lattice mismatch and having mixed phase. So the biggest challenge in this type of research is having a single crystal and a single phase uh, cubic nitride, and that's what we have demonstrated. The rest, the overlayer on top and a combination is going to have, of course, some seam effects when the growth fronts meet, but this is similar to lateral epitaxial overgrowth that we have done. We we do not expect any issues, and the defect density will just almost remain the same, except in the seam area where the growth fronts meet. Thank you, Albert. Yes, so there is another question about the growth of cubic GaN without reverting to hexagonal GaN, and this is indeed the case. So if so maybe I should just share the latest slide again. So basically, if we continue growing, if we continue growing, let me see here. I think everyone can see my slide still. Okay. So if we continue growing on top, we need to remove the oxide sidewalls. So this is what we have done. When you remove the oxide sidewalls, you can continue growing on top cubic. If you do not remove the oxide, you are going to initiate and restrict your cubic to a diamond pattern like this, and you are going to start a cubic, very defective hexagonal GaN on top. So basically, the answer to the specific question is yes, you can grow on top, but you need to remove the oxide. The oxide should not go above your pattern. So that's where this formula, where it tells you how thick your oxide should be, is critical. So right now, for example, we are looking into ways how we can grow this through removing of oxides, and we already succeeded mostly, and have a couple of patent applications.
Okay, is there any more questions at this point? Okay, it looks like that's it. Thank you so much for your webinar.
Thank you very much for all of you joining and listening. Thanks.